Thanks for inviting me to talk and for the nice introduction. I'm Daniel. I'm currently in Niterói, just across the bay from Rio. And today I'm going to tell you a bit about this notion of quantum computational advantage. Okay. So I think that this is a kind of very central paradigm for the times we're living in right now in terms of quantum technologies. But I actually think we're past the peak where this is kind of the most important thing. So I think like we should set our sights on the next thing now, and I'll try to convince you of that through the talk. So, you know, I was asked to give a kind of very broad, non-technical talk. So I'm going to start all the way with classical computing and what it means. And at the very end, I might get a little bit technical, but, you know, hopefully not too much. So this is what I'm going to talk about. I'm going to start by telling you what a classical computer does and what we understand this means and the sort of architectures that are behind it. Then we'll move to the classification of problems, right? So that's going to be complexity theory. And complexity theory is the theory that's going to give us confidence that quantum computers actually can do something that classical computers cannot. And I'm going to try to give you a flavor of what arguments there look like, right? How we can kind of ground our belief that quantum computers are doing something that's non-classical. Then I'll tell you a little bit about quantum computing and a very quickly definition of what a quantum computer is. But what I'll tell you here is that also when quantum computing was proposed, the theory was way, way, way ahead of experiments, of technology, right? Which sort of motivated the definition of some intermediate milestones. And that's where this kind of frontiers of quantum advantage is going to come in. Right, so these quantum advantage is going to be sort of intermediate milestones of, you know, what do we do with our quantum devices while we don't have full-fledged quantum computers. And I'll tell you a little bit about boson sampling, which is what I work on, and how it fits in this kind of broader picture of quantum advantage. Yeah, and then kind of wrap up. So let's start with what a classical computer is, okay? Oh, and by the way, feel free to interrupt me and ask questions at any moment. Yeah, so what a classical computer is, right? So we're going to compute with bits, billiard balls, and crabs. So, you know, not surprising to anyone, in a classical computer like this one, information is encoded in bits, right? Zeros and ones. And these bits are processed by logic gates, right? So you can think of these logic gates as functions that takes bits as inputs and produce bits as outputs, okay? And a classical computer is nothing more than a very, very, very big circuit of these things, okay? So now we don't usually have to think about classical computers at this level. And the reason is that, you know, any chip here in my computer has like trillions of these kind of tiny operations. So you would go crazy if you try to understand it at that level. So we've kind of developed several layers of abstractions that end up in like operational systems and stuff. But as you'll see, like in quantum computing, this is kind of the level we're at right now, right? We're kind of still talking about manipulating the qubits one by one. So at the fundamental level, this is what a classical computer looks like, right? A very big circuit of these things. Now, so far this is kind of abstract, right? So what do these mean? What is the sort of physical system, the physical architecture that's going to embody this classical computer? And in complexity theory, in theoretical computer science, right, there's a conjecture or kind of a thesis, which is the Church-Turing thesis, that says that the physical system doesn't matter too much, right? In what sense? It says that the collection of problems that you can solve in principle is the same for all reasonable, like that word's doing some heavy lifting here, but for all reasonable models of computation. Okay. And what this means, and we've kind of seen this play out over time, because, you know, way back in the beginning, in the 50s and 40s, you know, kind of classical computers were built out of these vacuum tubes. And, you know, like it's basically a circuit of the type that I wrote before, but using these kind of vacuum tubes as kind of carriers of information. And sometime later, the transistor showed up. And, you know, this led to this kind of race of miniaturization, right? So now you know, in the 70s, you could kind of pack a few thousand transistors in a chip. In 2010, which is already a very kind of outdated number, you could pack like 500 million transistors. But, you know, the fundamental model of computation, of what the computation is doing, is the same as the vacuum tubes. It's just that you would never be able to fit 1 trillion vacuum tubes in a chip this size, right? So it's a matter of difference in technology and feasibility, but not a difference in the sort of foundational definition of the sort of model of computation. And, you know, there are, like, the transistor won for kind of economic reasons, right? Now, there are other proposals that are maybe a bit more exotic. So there's this proposal by Fredkin and Toffoli of doing classical computation based on Newtonian mechanics. So what you do is you have like these tunnels, and you know, some of them, if the particle is going through some of the tunnels, you call that a 0, and if it's going through some other tunnels, you call that a 1. And just from the sort of laws of classical mechanics, of Newtonian collisions, Newtonian mechanics that describe how collisions work, these kind of geometric shapes perform computation for you, right? So you can kind of describe a set of logic gates that's based just on this kind of tiny balls colliding in these tunnels. Now, of course, this is theoretical, right? This is like, you wouldn't do this for practical reasons, but it's the same computational model that you can build out of this. And, which I find maybe a bit surprising, also with crabs, right? So hence the title of my talk. Because in, you know, what does crabs have to do with it? In 2011, a group in Japan showed that, you know, you have like these soldier crabs, and they move in these kind of swarms, these clusters, and when two clusters meet, the way that they interact processes information, acts like a logical gate. So you could, in principle, construct a classical computer out of kind of millions of swarms of tiny soldier crabs. You know, like in, and they did this like experimentally in what seems like a very good use of public funding. And yeah, so super exotic. You wouldn't do that. But again, the point here is that the physical system doesn't matter if you want to define what a classical computer is. But that's not quite true, right? And now we're going to move into the sort of a next layer of the definition, because we don't actually care just in being able to solve the problems. We want to solve the problems fast. So now we are going to add this extra ingredient of efficiency. Okay, and this leads to another thesis, which is the strong Church-Turing thesis. And this one says that all realistic physical models of computation, and again, realistic physical models is doing a lot of work there, are computationally equivalent. Now, what do I mean by this? You know, equivalent in what sense? So here, equivalent is going to mean in their asymptotic capabilities. Okay, what do I mean by that? We're going to need the definition of efficient, what it means to solve a problem efficiently. And for that, we're going to invoke a separation between polynomials and exponentials. Okay? Now, why? Because we know that polynomials and exponentials have fundamentally different asymptotic behavior, right? So asymptotically, any exponential grows faster than any polynomial, right? We know that eventually that's true. So to illustrate, right, if you have like these two functions, 100n and 2 to the n, if n is 10, they are pretty much the same. But if n is 100, the first one is just a measly 10,000, but 2 to the n becomes kind of pretty gigantic, right? So any exponential wins over any polynomial. Now, there are many examples of that. Well, you know, the pandemic was one kind of pretty impressive demonstration of the power of exponentials, right? There's also some story about the invention of chess, that the inventor of chess asked for like 1 grain of wheat for the first square, and 2 for the second, and 4 for the third, and 8 for the next one. And, you know, the king said, oh, that's nothing. And when you actually add that up, 2 to the 64 grains of wheat, or whatever it was, is more than India had produced. So, you know, that's another kind of known example. But my favorite example of the power of exponentials is this one. So this is a kinetic sculpture. I think it's at MIT. And what's going on is that here you have like a motor that's rotating at some reasonable speed. And it's connected to this kind of set of gears. And what happens is that each gear rotates 5 times more slowly than the previous one. And there are, I think, maybe 10 or 15 of them. And the last one is stuck in a block of concrete. Because the point is that the last gear will take more than the age of the universe to perform a full rotation, just because of the power of like how quickly the rotation speed decays. Okay, so good. This, why we care about this polynomial versus exponential separation. Now, having defined this, what we're going to do is say, look, a computational problem of size n, we're going to say that it can be solved efficiently if it can be solved in a number of steps that grows only as a polynomial in the size of the problem. And here, the size of the problem, you can think like very abstractly, any number that measures how big the problem is, right? So if you want to multiply two integers, the size of the problem can be the number of digits in the integers. If you want to say invert a matrix, the size of the problem could be just the size of the matrix. Some, vague thing that captures how big the problem is. And the thing is, you're going to say that you can solve it efficiently if you need an amount of resources, which you can think of as number of computational steps, but also in terms of memory, energy, or whatever physical resource you care about, that grows only as a polynomial. Otherwise, if you can show that that problem requires exponential effort, then it cannot be solved efficiently. Okay? So with this definition of the word efficient, technical definition, we can now restate the strong Church-Turing thesis, which says that the set of efficiently solvable problems is the same for all realistic models of computation, right? So this is saying that, it doesn't matter if you're using billiard balls or crabs or transistors, they're going to be only polynomially related to each other. And this thesis is what quantum computing, in a few decades ago came to sort of upset a little bit, right? Because quantum computers, apparently, as far as we can tell, can solve some problems efficiently that classical computers cannot, right? So quantum computers are the first serious threat to this strong Church-Turing thesis. Okay, so now I want to give you an overview of why that's the case, right? So what is the theory that grounds our belief that quantum computers can do something? And one kind of take-home message that's going to be very important that I think sometimes even people that work on this sometimes forget, is that it's not enough to show that a quantum computer does something. You have also to show, does something efficiently. You have also to kind of give good evidence that a classical computer can't do that thing, because classical computers are much cheaper than quantum computers, right? So if there's something that a classical computer would be perfectly or well suited to do, you wouldn't need a quantum computer for that. So most of the hard work in this field is giving arguments that classical computers cannot solve certain problems. And to give you an idea of how those arguments go, I need to talk about complexity theory. Now, this is going to be alphabet soup a little bit. You're going to see a bunch of letters and acronyms, and it's going to kind of look confusing, but don't worry about it too much. I'm going to kind of tell you which ones are more important to pay attention to right now. So basically what happens is this. After we define this notion of efficient, right, in terms of polynomial versus exponential, over the decades, theoretical computer scientists have built this big landscape of complexity classes where you join together computational problems by how hard they are to solve, for example. Right? You say, oh, there's going to be a bunch of them that are easy to solve, a bunch of them that are hard to solve, and 1,000 different variations of that question. And this leads to a kind of very complicated landscape of this classification. Now, this is the simple one, right? Bunch of letters, but this is the simple one. This is called sometimes the big one is the zoo, and this is the petting zoo that has we take a child to the zoo and there's kind of a small zoo with like rabbits and kind of tiny harmless animals. The big one that has the lions and tigers has like thousands of different complexity classes. Okay, so that's kind of pretty horrible. I'm not going to show you that. Let's just talk about these kind of small rabbits here. So I'll tell you a little bit about some of these concretely, just to sort of illustrate. And the first one, most obvious one, is going to be a complexity class known as P. Okay, P stands for polynomial time. So, obviously what it means are problems that can be solved efficiently by a classical computer. Okay, pretty straightforward. So you can imagine a classical computer that looks like this, and if there is a circuit that looks like this, but only has a polynomial number of these gates that solves a particular problem, that problem is in P. Okay, that's the definition. And we know many problems that are in this class. So for instance, if you want to decide whether a number is prime, if you want to compute the determinant of a matrix, if you have a map and you want to color it with two non-adjacent colors, assuming that's possible, if you have like n integers and you want to find the maximum one. So all of these problems and a huge heap of other problems, any problem that you can think of that you can solve in polynomial time, typically quadratically or like cubic time at most, you're going to fit in this big complexity class called P. And these are the ones that classical computers are perfectly good for. Okay, so, you know, but one class doesn't do a lot of classification, so let's look at the next one. And this is a pretty famous one, which is called NP. The name does not matter. It comes from historical reasons that are kind of super obscure and opaque. But it's NP, and basically it's the class of problems where, you know, if you have a solution, you can check that the solution is correct, regardless of whether the solution is easy to find, right? So it might be a very hard problem to solve, but if I give you the solution, you can check that the solution is right. And that's going to define this class NP. Examples. Factoring is a famous example, right? So if I ask you, what are the prime factors of an n-digit number? One direction here is expected to be really hard. And in fact, you know, if you have like the biggest classical supercomputer, can only factor a number with at most 250 something digits.
Okay, it's okay. Just to know, like, when you say that you can check it with the classical computer, you mean you are checking the problem that you solved using a quantum computer?
Not necessarily. We haven't.
Okay.
I haven't talked about quantum computers yet.
Yeah, that's what I want. Okay.
Yeah, no. Factoring will actually be one example where a quantum computer can solve. But in fact, we don't think quantum computers can solve all of these problems, right? So it's going to include problems that, you know, someone somewhere gave you the solution and you can check that the solution is right, without having to make reference to who found the solution for you.
Okay.
Okay? So just, you know, in principle, if you had the solution, you could check it. That's all that you require for the definition. Now, factoring is one of them, right? Because, you know, this direction is expected to be really hard. The other direction is really easy, right? So if I tell you, oh, no, actually, those two are the factors of this number, you can just multiply them together in your calculator, and that's a really easy thing to do, right? So those NP problems are the ones that have this expected asymmetry between checking the solution and finding the solution. Now, and this is going to be a recurrent thing throughout the talk, and this is really important. No one can prove so far, I mean, no one has been able to prove so far that factoring is actually hard, right? So when I say that this is hard, this is expected to be hard. It's expected to be hard so much that there are kind of cryptographic schemes for like sending messages online that are based on the fact that this is hard. It's expected to be hard so much that people have been pouring a lot of money and effort into quantum computers, and one of the reasons is because quantum computers can solve this problem, and classical computers are not expected to be able to. So we can't prove that it's hard, but there's a lot of accumulated evidence that points towards the fact that it's really hard. But it's still logically possible that tomorrow someone will come with an algorithm that solves factoring in polynomial time. Okay? And this is going to be a recurring thing. Now, before I tell you why, let me give some other examples of more interesting NP problems. One is very famous, traveling salesman, right? It says that, you know, if you have a list of n cities and the distance between them, I can ask you, oh, is there a path with length smaller than x kilometers that visits all those cities? Right? And that's an NP problem because, you know, there might be exponentially many different paths. And, you know, maybe the only way to find a path that is sufficiently small is kind of try all of them. And there are exponentially many of them. So it might be super hard to solve. But if I give you a path and say, oh, look, this path has many than x kilometers, has less than x kilometers and visits all those cities, you can check that very easily. Another example, if I give you a map and you have to decide whether you can paint that map with only 3 non-adjacent colors, right? So 3 colors, but you can't have 2 neighboring regions painted in the same color. Again, deciding whether this is true, whether this is possible, is really hard. as far as you can tell. But if I give you a painted map, you can look at it and say, well, yes, it is painted with 3 colors. Or in this case, in the map of Brazil, it cannot be painted with just 3 colors. Okay? But the map of Australia can be painted with 3 colors. Okay? So if I give you a painted map, you can look at it and say, yes, okay, fine. You can very easily, in polynomial time, check that it is colored. Okay? But finding that coloring might be really hard. Okay. And the thing is, there are thousands of problems of this type. And, you know, one very important, very central question is whether these two things that I've described you are actually different. That thing we have not been able to prove. This is one of the most important open problems in mathematics. It's literally $1 million question because it's one of the Millennium Prizes, Millennium Problems from the Clay Institute, and it's really worth $1 million. And, you know, it's just deciding whether there actually exists some problems that are of this type, that you actually need an exponential effort to solve, that cannot be solved in P. Now, if this was true, if P turns out to be equal to NP, and we don't know, I think it would be like one of the most powerful results in history, because it would say that merely from the ability to check whether a solution is correct, you also have the ability to find that solution. And that seems super weird, right? That seems very unlikely. Now, again, we can't prove whether this is true or not. However, you know, we can think of the several decades that people have been trying to solve this problem, and the fact that there are thousands, like 2,000 or 3,000 different problems from mathematics, physics, biology, logistics, chemistry, that are all of the type that if you solved any one of them, you would automatically solve all of the others, right? There are thousands of problems for which that is true. And all of these kind of researchers have been trying to solve these problems over the last several decades, and not even a single one of them has fallen. That is accumulated evidence towards the fact that these two complexity classes are actually different. Okay? And this is a small instance of a more general behavior of these complexity classes, where it's really hard to prove that they're separate. Okay? So let me go back to this kind of big map here of all of them. Now, we've talked about P and NP. They're here. Okay? But there are many others. And in this diagram, upward lines mean provable containment. Okay? So you can say that, oh, P is contained in NP. The thing that you want to decide is whether it's different from NP, right? Or whether there's someone here that's not here. And all of these lines are provable containments. You can prove that one is included in the other, and that's relatively easy. And just to kind of give you a flavor, we talked about P, which is polynomial time, which is down here. There are other problems, for instance, exponential time. So those problems on the top there are the ones for which you need an exponential time to solve. Okay? You have P space, which is polynomial memory. So it says, oh, you know, take as long as you want, but only use polynomial memory to solve this problem. That's what P space means. And L means logarithmic memory. Okay? And why am I telling you this? Not because these are going to be important, but because though we can prove this kind of containments from bottom up, there are very, very few provable separations. And the only ones that we can prove is, for instance, that P space is not contained in L. That one you can prove. Or that exp is not contained in P. That one you can prove. So you know that P is strictly smaller than exp that's all the way there on the top. But all of the other intermediate ones, even P and P space, which look pretty separate in this diagram because you have NPs right here, right? So pH and char P and P space are all much more complicated than NP. Even this you cannot prove, that P is separate from P space. Okay? So this is just to kind of show you, like, we can prove that there are some problems that need exponential time, but we know kind of preciously little about how to separate these guys. And the reason I'm telling you this is because at the end of the day, since you cannot, or at least it's very hard to prove that these things are separate, you ask, well, how do we do science to this then, right? Like, what do we do? You can't prove that these problems are actually hard. Do we then just do nothing? And the point is, the fact that this is hard kind of gave rise to this type of argument, okay? So imagine that you have some statement and you say, oh, you can prove that statement is true implies some dramatic consequence for these complexity classes, right? So you assume that they're kind of all different. And if X is true, they would all collapse and be actually the same thing. You'll say, well, if I can prove that for some statement X, then this acts as evidence that X is unlikely to be true, right? Because you have strong expectations that these complexity classes are different. For example, if you have an efficient classical algorithm for 3 coloring, P equals NP. Okay, that's one example. And you can think of this as in kind of motivation for proving statements of this type in 2 ways. One of them is a heuristic, right? So if you kind of are doodling in a restaurant and you think you've found a polynomial time algorithm for 3 coloring, you probably haven't, because that would be an earth-shattering result that's probably not going to be proved in a napkin in the restaurant. So you should probably kind of take the safe approach and look for where's the mistake. Or, which is apparently has become a much worse problem now, if some person tells you that ChatGPT talked with them and told them that their algorithm is fine for proving that P equals NP, like you can probably expect they're wrong. Right? So this can serve as a sort of heuristic. You say, this would be such groundbreaking results that you should be very skeptical of them. But there's another thing, which is that these give more robustness to the structure of complexity classes, right? In the sense that rather than having like a weird collection of loosely defined problems and classes, every time that you prove that, these 2 things are equal, contingent on this thing being equal and so on, you're kind of tying them together, right? So today, someone finds one algorithm, for any of these NP problems, everything collapses, right? Because you're kind of tying them together. And the story of quantum computing also kind of fits in that logic, because you can show that efficient classical simulation of a quantum computer would imply a collapse of the polynomial hierarchy, right? Polynomial hierarchy is this guy here. Doesn't matter. The details don't matter, right? It's just supposed to be an infinite tower of complexity classes. Don't worry about it. But the fact that this does not collapse is not as strong as P equals NP, right? So if you prove that you have a classical simulation for a quantum computer, that doesn't imply that P equals NP, but implies like the next weirdest thing in the list, let's say. So you can show that efficient classical simulation of quantum computers implies very weird consequences for these complexity classes. And this is one of the things that grounds our belief that quantum computers do something important and interesting and really hard, right? Again, at the end of this day, we're not going to be able to prove that fact. No one has proven that a quantum computer is better than a classical computer. It's only proof contingent on this, okay? This is one of the main take-home messages. Now, the interesting thing is that this remains true even for some very rudimentary quantum computers. Some very simple quantum computers that are not universal, that are not full-fledged, that are not very big, they also have this property. And this is the thing that I'm going to talk about now. So this is where this kind of quantum advantage or quantum computational advantage story is going to come in. On like very experimentally friendly devices that have this property, that are not full-fledged quantum computers. Okay? What? This property that they cannot be simulated, right? So this property that if you were able to simulate them on a classical computer, everything would be weird and collapse. Okay? Before I tell you that, I want to describe a very simple physical system. So let me talk a little bit about quantum computing with qubits and bosons, but for very interesting reason, not with fermions. And I'll tell you why shortly. So, very quick, one slide timeline of the origins of quantum computers. So, quantum computers, the idea arose in the 80s. Benioff and Manning talked about using quantum systems for computation. But there's a talk by Feynman, which is considered to be one of this kind of first places where this idea was kind of fleshed out a bit more seriously. And what he noticed was, well, quantum systems seems to be exponentially hard to simulate on a classical computer because we would like to simulate them, and it seems to be hard. What if I used other quantum systems to simulate my interesting quantum systems, right? So this was the first idea of a quantum simulator. where a quantum device would solve the computational problem of acting like a different quantum system, behaving like something else. And this is the sort of idea of a quantum simulator. And this was formalized a little bit later with Deutsch in the idea of what a universal quantum computer is. So when we talk about what a quantum computer is today, it's traced back to this kind of definition by Deutsch, more or less. So what is a quantum computer? It's basically the same thing that you've already seen for a classical computer, which is going to be a circuit out of these logic gates, except that now everything lives in a Hilbert space, right? So basically your input is going to be, rather than a bunch of bits, is going to be a bunch of very simple quantum systems, which we're going to call qubits. Could be like spin half particles, could be photon polarization, it doesn't matter too much. And your circuit of logic gates are going to be a sequence of a polynomial number of unitary transformations. And they have to be unitary transformations because they have to be kind of solutions to Schrödinger's equation. And the measurements, you know, the output of the circuit is just going to be measurements that you perform who are kind of governed by the Born rule. Okay, so this is what a quantum computer is, essentially. And what can it do? You know, from the beginning, people noticed, like Shor and Feynman and Lloyd and some others noticed that there's a bunch of tasks that these devices can perform in polynomial time, like factoring is one of them. Computing discrete logarithms, quantum simulation, searching in unstructured databases, solving some aspects of linear systems. There's some fine print here, doesn't matter too much. And, you know, hopefully many, many other things to come. Now, we know that quantum computers are good for a very specific set of things so far. That set of things is growing, right? But it's not just like magic powder that you put on a classical computer and it becomes super useful for everything. Now, but again, notice factoring, I've told you that we don't know if factoring is really hard. We don't know if any of these things are really that hard. Right? So our belief that quantum computers do something interesting is the belief that these things are things that a classical computer cannot do. But that belief is predicated on that structure of complexity theory that I talked about before. Now, the thing is, if you look at these numbers, 94, 96, you know, the thing is that the theory here was way ahead of experiments, right? Because the sort of like quantum computer that you had at the time, where you could kind of control these quantum systems individually, the biggest ones had like 3 qubits, 4 qubits, 5 qubits, right? Again, there are trillions of transistors in your classical computer because classical computing has like 70-year head start over quantum computers. But at the time you had like, you know, Shor said, oh, you know, when you can get me like 10 million qubits, you can factor a very big number. And the experimentalist said, good, we have 4, what can you do with that, right? And you can factor, and I think it was in 2009 maybe that they factored 15. And they showed that it was like 3 times 5 with high probability. So yeah, you know, like at the time, quantum computers were really tiny, right? Because controlling these quantum systems individually is really hard, right? So this is kind of a very important kind of technological limitation. And then what, you know, people have roughly in 2012, what some people, in particular Scott Aronson and Alex Arkhipov, noticed was that, well, let's maybe flip the question around, right? You know, like maybe factoring is in the future, maybe it's like 100 years in the future, and maybe we're not going to live to see it because you need 1 million qubits and we only have 5. So let's then change the question and ask, okay, what is the simplest task, the smallest task, the most experimentally feasible task that a quantum computer could do that a classical computer could not do in reasonable time? It doesn't matter if that task is useful for something, leave that for later. Right, so right now, let's try to at least say, you know, maybe in the future, if we happen to have 50 qubits, for example, is that going to be doing something that's already hard or not? Right, so that was the motivation for this field of computational advantage that arose in 2012. And I'm going to tell you one example of task for which this is true, one very simple physical system that's going to perform some task that a classical computer cannot do, as far as we can tell, up to those conjectures of complexity theory. But before I tell you that, let me describe what the physical system is. So, very simple, at the beginning, this is a particle. For now, any particle, doesn't matter, okay? And it travels along these straight lines. You know, we're gonna call, if it's following the horizontal line, we're gonna call that a 0, and if it follows the vertical line, we're gonna call that a 1. And that thing in the middle is a beam splitter, right? So what a beam splitter does is that it puts a particle in the superposition, of exiting in these two modes, all right, traveling in these two directions. Very simple physical system. Everyone's familiar with that. Now let's talk about a slightly less simple quantum system. You're going to take the same physical situation, but now you're going to use two particles rather than just one. So you're going to take this beam splitter, and you're going to throw in two particles, and you want to see what happens. Okay? Now here, I need to differentiate between bosons and fermions. Okay? So now we know that particles in nature comes in two varieties, bosons and fermions. And for bosons, the wave function is going to be symmetric, and for fermion, it's going to be anti-symmetric. And that's going to have remarkable consequences for that experiment. So let's look at bosons first. Okay, so bosons are initialized in that state, that's symmetric, and just by virtue of the symmetry of that state, the output is going to look like this. And what this is saying is that 50% of the times, both bosons come out together here, and 50% of the time, both bosons come out together there. And this is known as the Hongo-Mundell effect. Okay, and basically what it says is in this experiment, the bosons always leave together. Right? This is kind of the smallest example of this kind of paradigmatic bosonic bunching effect. You know, bosons tend to bunch together. Now, this generalizes a little bit, and if you replace this beam splitter here by, rather than being just like 50-50 beam splitter, where the probabilities of exiting in each port are 50%, you make it kind of an arbitrary unitary matrix. You can show, and the details don't matter too much, but you can show that the probability that they leave separately looks like this. So if you look at the matrix A, B, D, C, the probability looks like this. And this almost looks like the determinant of that matrix, right? Except that the sign here is wrong. This function is known as the permanent. So this is the permanent of that matrix, okay? Let's leave that permanent in our memory for a few slides. I'll get back to it shortly. But let's stop to talk about what fermions do, right? So if you have fermions, the wave function is now, rather than being symmetric, is anti-symmetric. And just from that anti-symmetry, the probability that they leave separately is given by this thing, which is now the determinant of that matrix, right? But if that matrix is unitary, as it has to be, this determinant, the absolute value of it is 1. Okay? Which makes sense, because this is nothing more than the Pauli exclusion principle, right? Fermions can never leave this interferometer. They can never leave the interferometer together because they're fermions, right? So bosons always leave together, fermions always leave separately, right? Okay, good.
Can I make a question? So when you showed one particle in the beginning, it seemed like the input was in the 0 state.
Yeah.
Whereas when you put the two particles, the input seemed to be like a superposition. There. So you have both zeros and ones for the first.
No, this is just the symmetrization of one particle is entering in input 0 and the other one is entering as in input 1, but you don't know which is which because they're identical.
I see.
So that's just kind of taking the symmetric superposition of all those possibilities.
Okay.
And if you take the anti-symmetric, then you get the same conclusion, but for fermions.
Okay, good. Thanks.
And just from that sign, follows kind of this very dramatic difference in behavior. Now let's scale this up even more. Let's look at a very big experiment where you have a bunch of these bosons, and they're going to pass through a very complicated circuit made out of these individual elements, these beam splitters. And what you can show is that, if you have some input state S, and they propagate here, and you detect at the end where they arrived, so you're measuring the Fock basis, so you want to know where each boson ended up, and that's some state T, you can show that the probability that this happens is always given by the permanent of some matrix. How you build that matrix doesn't matter too much right now. Okay? You can ask me if you want, but it's like, okay. But the point is that these transition probabilities in these bosonic linear optical systems, right? So this is just what linear optics means, are given by permanents of some matrices. And, in the same way, if you talk about the larger version of the experiment for fermions, the transition probabilities are given by determinants of some matrices. Now it's where it gets interesting, because you can ask, well, how hard are these things to compute? The determinant is in P, right? Polynomial time. Determinant is super easy, right? You take like n squared or n cubed operations roughly to compute the determinant of a matrix, if you're n cubed if you're very sloppy. Okay? However, the permanent, which remember, looks a lot like the determinant, it just doesn't have those minus signs, is way up there. Okay? So P here, NP here, something that's like several layers above those really complicated NP problems is a class called Sharpie. Doesn't matter too much, but that's where the permanent lives. Okay? And what this says is that, you know, non-interacting bosons, or bosonic linear optics, is hard to simulate on a classical computer up to those conjectures that I mentioned before. Whereas non-interacting fermions are easy to simulate on a classical computer, right? And I personally find that fascinating. Like, that's the thing that I've been thinking about since my PhD. And my PhD, like, the title is The Computational Power of Non-Interacting Particles, because like half of it is about fermions and the other half is about bosons, because I think this is like super interesting, which is this connection, like fundamental connection between the computational power of a physical system and the nature of identical particles, just like being bosons or fermions. But what happened is, like in 2012, Aronson and Arkhipov noticed this, right? And they said, wait a minute, like these bosons, it's a very simple physical system, right? In the sense that, you know, imagining an experiment with 1,000 qubits back in 2012 was absurd. Imagining an experiment with some number of photons at the time, if you're going to do this with photons, that was much less absurd, right? The technology was much more ripe for a physical system, like a physical model of this type, than for a universal quantum computer. So what they noticed at the time was like, look, can we leverage then this distinction between bosons and fermions to provide a task that this very simple quantum device, which is not expected to be universal for quantum computation, right? So this kind of thing, you don't expect to be able to do quantum computation fully just with this, right? This is a kind of very rudimentary quantum system. But they said, can you use this can you propose a task that this system can solve that a classical computer cannot solve, that is based on this fact? And, you know, 120 pages later, they managed to prove that up to some conjectures, right? It's really complicated. Like, it's not easy to go from like this fact to these are automatically hard to simulate. That, like, there's a lot of work done there, but that's basically what they showed. Okay? So this became known as boson sampling. And this is what I'm going to tell you in a bit more detail now. So this task of boson sampling is the following. Again, just kind of formalizing a little bit the thing that I've already said. You start with a bunch of bosons, photons in practice. You start with a bunch of photons, and they can travel in these kind of different directions, and they pass through this interferometer, which is just kind of a big network of these beam splitters. And, you know, you measure where they end up. And you do this many, many, many times, and you accumulate statistics, right? So this is going to be the probability distribution associated with these outcomes. And the statement that Aronson and Arkhipov did in 2012 was, producing a sample from this output distribution is a computationally hard task for a classical computer. That's what they showed. Up to conjectures. I'm never going to tire of saying up to conjectures at the end of my sentences, right? Up to those conjectures. And, you know, kind of experimentalists already had small versions of those experiments at hand. They were kind of really looking for something to do with those experiments. And, you know, like a few months after that proposal came out, 4 different groups demonstrated the first experiments of kind of first small proof of principle version of this thing. I was involved not in actual experiments. I didn't go into the lab because I would like set fire to something or something. But I was involved in kind of the analysis of one of these experiments together with the people in Rome, my PhD advisor and me. And basically all of them are just kind of instances of this thing that I described, right? So you have like these interferometers, and you have up to 5 of these modes, and using up to 3 photons. Okay, now is 3 photons hard to simulate on a classical computer? Of course not, right? 3 photons is trivial. But these were like the first proof of principle experiments. And at the time, what people noticed was that, you know, if you got to the point where you're doing experiments with like 50 photons, then you would be getting into like the regime of something being actually hard for a classical computer. Right? You try to compute the permanence of a 50 by 50 matrix on this computer, it can't. That's already too big. Okay? Now, compare that with needing 1 million qubits for like factoring with Shor's algorithm, right? So at the time, people looked at this as, no, you know, 50 photons is in the near future much more kind of reasonable than 1 million qubits. And then people really started working on this. And I think this was really important for kind of pushing the field forward. And sometime later, a group in China showed an experiment with 20 photons in 60 modes. Okay? And this was the largest experiment that I could find using this original boson sampling proposal. Now, there's a thing here, because one of the things that's experimentally challenging for this are the photon sources, right? So having a source that spits 1 photon at a time very reliably, that's very hard. So then at that point, people said, you know, wait a minute, what if we use different states of the electromagnetic field? Rather than using Fock states, which have well-defined photon numbers, what if we use things like coherent states or like squeezed states? So this gave rise to a different thing, which was a variant of boson sampling, which became known as Gaussian boson sampling, right? Which uses these Gaussian states. And using this variant of Gaussian boson sampling, this was one of the experiments that was done in China. I actually visited this lab. And just to give a kind of, this uses, I think, 50 photons in the end, in like 100 and something modes. Right? Which means that there are like 100 different paths that the photons might take in this gigantic, horrible thing that you're looking at here. Right? This was a kind of really impressive technological achievement, like aligning and setting up all of these things. So, you know, experiments then quickly became larger. And I was taken by surprise a few weeks ago. I wasn't really taken by surprise because I had heard, like in the grapevine, I had a friend who went to a conference where he had seen this paper, but when it came out on the archive, I was it was super impressive, where a group in China made an experiment in this Gaussian boson sampling setup with 3,000 photons in 8,000 modes. This is gigantic, right? This is extremely impressive. Compare it with the 3 photons in 2012. Right? This is an amazing evolution for this field in like 10 years. Right? If you had asked me whether this was possible like 6 months ago, I would say like, that sounds absurd. Okay? And there's a bunch of interesting new ideas that they used here. So, you know, this Xanadu guys in Toronto, they looked and said, look, having 100 different directions in which the photons can move is really hard. And therefore, they replaced this kind of spatial degree of freedom, or photons move that direction or that direction. They replaced it by a temporal degree of freedom, where they say, you know, the degree of freedom is the photon arrives now, or a little bit later, or a little bit later. So they encoded information in this kind of what is known as time bin encoding. And then they managed to kind of perform larger experiments. This experiment from a few weeks ago mixes both things. Right, so the way that they get 8,000 modes is by a combination of the photon can arrive in that direction or that direction or that direction, and right now or a little bit later. Right, and by combining these 2 degrees of freedom, they managed to make like this gigantic experiment. Now, you will notice that I've added this extra column here, right? And now is where I'm going to talk, like plug my own work a little bit. So I've added this extra column here, which is the ratio between the number of modes and number of photons. Okay, so you'll notice that, you know, they are performing these experiments with a huge number of photons, but the number of modes of the directions that the photons can move in is like roughly twice, at most twice, the number of photons, right? However, there's a caveat here, there's a fine print, because the theoretical result from 2012 required the number of modes to be quadratic in the number of photons, to be at least n squared, okay? Now you go to one of these experiments and say, oh, you have 3 photons, that's 3,000 photons, that's very nice. Can you do an experiment that uses 9 million modes? And they're gonna kind of laugh you off the room, right? They'll say, that's absurd, please never come back here, sir. So, you know, like, this regime is awful for experiments. And the experimentalists have completely ignored this constraint, right? And they're right to do so. So what I'm going to kind of spend the last 10 minutes telling you about is some recent work that I did with some collaborators where we kind of removed this constraint. And I'm going to kind of try to give you a flavor of what are the things that you need to prove. Okay? So let me tell you a bit why in the original paper those were kind of necessary. Okay, that constraint of having many, many more modes than the number of photons. Now, there are mainly 3 reasons, and they're kind of technical, but it's not too bad. So one of them is that if you take a very big matrix, unitary matrix, right, and you look at tiny submatrices of it, they look Gaussian. They look like they're taken from the Gaussian ensemble, okay? And Gaussian ensemble is extremely well studied in random matrix theory. Right, so they said, oh, this is a nice regime because since these matrices look Gaussian, I can just kind of throw a bunch of random matrix theory at this and use a bunch of known results from there. Right, so that was one of the reasons they wanted this kind of ensemble to appear. The second reason is both experimental and theoretical, which has to do with collisions. So if you have a few photons in a huge number of modes, what happens is that these photons will tend to come out very separately, right? They'll come out very separate from each other. A collision is when you get 2 photons coming out in the same detector, right? And this is very unlikely if you have many modes. You can prove that. Now, this is technologically, it's good because it's much, much easier to differentiate between 0 photons and a single photon than it is to differentiate between a single photon and 2 photons. Right? Differentiating between a single photon and 2 photons is a completely different level of technology. So these collisions for experimentalists back in 2012 were really bad. But also for the theory, it's easier because if you have these collisions, remember that I told you that these transition probabilities are given by permanence. If you have collisions, your permanents start having repeated rows and repeated columns. And that means that the problem might become easier to solve. Remember, we want this to be a very hard problem because we want quantum computers to perform really well. If the problem starts becoming easy, your quantum computer starts becoming useless. So these collisions are bad for that reason. And there's some other technical reason that the outcomes kind of all look the same, right? So you can say, oh, if I prove that one outcome kind of looks very hard to compute, that automatically becomes true for kind of all of the others. However, those things were chosen just because they made things easier to prove in 2012, right? So back then you said, oh, we're only going to do experiments with 3 or 5 or 10 photons in the foreseeable future anyway. So let's just prove this thing in the easier case and leave the hard case for when it becomes a necessity, right? And right now it is a necessity. Because this is way too stringent for experiments, right? This constraint. So here enter our result, where we give evidence that this model of boson sampling remains hard even if you have the number of modes only twice the number of photons, which matches exactly what experimentalists are doing, right? So basically what we're doing is we're patching the claims in the experiments, right? We're saying, you know, retroactively, experimentalists, what you're doing is fine. And they'll reply with, you know, we didn't ask you, we don't care. We're just going to do this because that's what we can do. And what we're saying, like, yes, okay, but you keep on doing that because it's fine. You know, if skeptics come to talk to you, tell them to talk with us because we can prove that that's fine. That's basically the Lord kind of idea of this result. So this involved solving a few new challenges, just to give you an idea of what happened, kind of very briefly. One is if the number of modes is small, then the kind of entries of the matrix look very correlated. So just to give you an idea of what's going on, right? If you have a very big matrix and you're looking at a tiny submatrix of it, if this big one is uniformly random, it's unitary, this big one looks, the small one looks Gaussian, right? That's what I said that they used in 2012. Now, sorry, that's not true anymore. You're now looking at a very big submatrix of a unitary matrix. And now you start seeing some constraints that come from the fact that this matrix, the big one, has to be unitary. And so all of its columns are kind of orthogonal to each other. And that means that all of these entries become correlated. and like all of the random matrix theory kind of goes out the window, and we have to do a bunch of new random matrix theory to take care of this case, right? So this involved like inventing some new results in random matrix theory to take care of like that kind of matrix. The other thing is that, you know, now collisions are likely. So remember that I told you that if the number of modes is very large, the photons tend to come out very spread out. Now you start to see a bunch of these collisions, right? So now the norm is going to be having more than one photon per detector, right? And then we had to prove that if you have permanents that have a few repetitions in the rows, that doesn't become too much easier. That's fine. And that's a very strong difference from the determinant, right? Because if you want to compute the determinant of a matrix, when you have two identical columns or rows, it's 0. The end, right? And for permanents, you know, it doesn't become much easier. We had to prove that fact. And the other thing, which is, you know, doesn't matter too much, but is now that rather than saying, oh, I've proved that one outcome is hard, therefore it follows that all of them should be hard. That was something that was true in 2012. Now we say, actually, you know, there are exponentially many different ways that the photons can kind of group together. And we have to prove that like most of these outcomes are hard, kind of, you know, one by one, let's say. So we had to kind of take this into account as well. But the main result, you know, just to kind of punchline, is that boson sampling is hard in this regime where the number of modes is only twice the number of photons, where experiments are done, to the same standard of proof that in the original paper. Okay, and I'm going to skip the next bit here. You can ask me if you want, but this kind of standard of proof is just saying that we haven't proven that boson sampling is as hard as the original case, right? It's a logical possibility that, you know, because this relies on some conjectures, so it's a logical possibility that the conjectures it relies on are true for the 2012 paper and are not true for ours. That's kind of still logically possible. But we can show that we can prove weaker versions of that conjecture. To this kind of same level of precision as in the original paper. This is a bit technical. I can talk about this if someone asks. So just to kind of conclude, and because I think I'm kind of short in time, basically the idea that I wanted to kind of tell you was that, you know, quantum computing promises practical computational benefits. However, it has been promising these practical computational benefits for the last 4 decades, right? And things at the beginning were moving relatively slow. I mean, super fast. All the experimentalists are awesome and they do very awesome work. But, you know, in the grand scheme of things, things weren't moving super fast. So this led to this invention of this kind of intermediate milestone, which was this quantum computational advantage, right? The idea was of finding a set of possibly useless tasks for which, one, a rudimentary quantum device built in our lifetimes could perform, right? So no waiting for 1,000,000 qubits for Shor's algorithm. Let's do this while we're still alive. But for which there is reasonable evidence that a classical supercomputer would not be able to do the same thing. And this reasonable evidence here has all of the field of complexity theory behind it. Now, this in our lifetimes, that's in the past, right? So this was the motivation in 2012. When the experiments had 3 photons, now the experiments have 8,000 photons, and you know, this doesn't make sense to talk about it in our lifetimes anymore, right? Now you can say, you know, it's not fully closed question. There are still some caveats in these experiments, but I think, you know, you can safely say that this will be settled in the life of like someone's cat or someone's dog, okay? Not our lifetimes. Well, our lifetimes as well, of course. But then I think that, you know, in my opinion, we kind of might be crossing the peak usefulness of this idea, right? Because we're entering a regime where, you know, the devices are becoming so complex that we're losing the ability to even tell whether they're working properly, which is kind of a disadvantage of this concept of computational advantage, right? You can say, you know, you kind of build a device and you say, yes, it has sampled 8,000 photons. You're like, yeah, cool, looks complex, I can tell, right? So we're kind of crossing this because we're now at the point where you say, yes, experiments are becoming huge. You know, maybe, you know, the number of photons went from 3 to 3,000, like that's 3 orders of magnitude in 10 years. So maybe 1,000,000 photons for Shor's algorithm is not absurd in given, you know, another 2 decades or so. So, you know, I think like at this point, the more timely question to ask is say, you know, this was a useful idea over the last 10 years. This pushed the field forward by a lot. And, boson sampling is not the only example. So the stuff that Google and IBM have done, they have announced their big quantum computers that have like 100 qubits, or IBM, I think, announced one with 1,000 qubits. And the type of experiments that they are doing are also of this same type, on this kind of computational advantage umbrella, where you say, oh, it's kind of some useful task, but it's kind of at least hard for a classical computer to do. And, this kind of really pushed these people to kind of work on this and develop these techniques and this kind of experiments. But now I think this is kind of outliving its usefulness a little bit. And now I think that the most timely question for people who like maybe are entering this field right now is, what do we point to next? Right, so maybe it's still a few decades until we get to Shor's algorithm. So what are the interesting things that we can kind of aim at doing before then? Okay, so yeah, that's what I wanted to tell you. Thanks.
Questions?
Thanks, Daniel. It was really amazing talk. So I have two questions. One is like, so the problem, you know the initial state, you know the final state, and you know the unitary, right?
Yes.
So you know all of these, and you want to find a classical algorithm that does that. So what is the algorithm? Like, it seems like basically you have to look at the matrix and.
Well, okay. So the thing that's hard is producing a sample from that output distribution, right? So you say, if I fix the input state and I fix the output state, then you can say, oh, I can compute the probability. I can't, because that's actually a permanent, but the quantum computer can't compute that either for technical reasons. So then the task is kind of a sampling-based task, where I say, produce a sample, like press a button in a classical computer and produce a sample that follows this probability distribution. That is the task. Okay. And that is hard.
Okay, so the second question is about the experiments. Like, well, okay, so M and N being closed, it's fine. But what about other sources of, so like, does the detection efficiency of the detectors play any role? Or like, in practice, you don't have a unitary, you are always going to have a CPTP map, so some noise, and you are not going to have like fully indistinguishable photons. So what are the roles of all these imperfections? Do they play an important role or not?
They do, right. Yes, those are all complicated things, and people have been working on them. So I have, for instance, I have papers where we show that if you only lose a few photons, it's fine. Or like if you don't detect them. I have papers where we show that if you lose too many, it's not fine. And there's a big gray area between. And that is one of the caveats that I mentioned. So someone could still say, look, these experiments, if you have like these many modes, if you have like a circuit like this, and you have, for instance, losses, right? What happens is that the losses accumulate exponentially, right? So if there's some probability that a photon is going to be lost at each beam splitter, that probability is going to, the probability that it will survive decays exponentially with the depth of the circuit, right? So, technically, that hasn't been solved, right? That's still a big problem, a big limitation in boson sampling. And it's one of the sort of fine prints that's kind of still open, like loopholes, let's say. However, there was a paper from earlier this year showing that you could also do boson sampling with a logarithmic depth circuit, which uses these kind of butterfly networks and stuff. So, people have been working on this, and, those are all important problems, and they have not all been patched. There's still kind of big thorns on the side of, again, I think that maybe the field as a whole is going to start leaving this idea behind before closing all of those problems. I think at some point it's going to be less relevant. But yeah, those are all important kind of points.
Hello. Oh, okay. So first, thanks for the great talk. Computing impermanent per se is like a Sharpie complete problem,
yes,
right?
Yes.
So that's, I think, the technicality that
yes, that's right.
So there are a lot of other Sharpie problems that are very cool for physics. For example, I don't know, estimating partition functions is a very good example of that.
Yeah.
Is there any sign that there is some kind of quantum algorithm that estimates, say, I don't know, other Sharpie complete problems with noise like we have for the permanent? Like,
no. So actually, one caveat here is that, you know, the probability is given by a permanent, right? However, the permanent is not, the probability is not an observable, right? So if you try to build a quantum device that computes the permanent for you based on this, that doesn't work, right? Because what happens is that you're going to have a bunch of probabilities and they're all going to be very tiny, and you're going to have to repeat the experiment exponentially many times in order to get decent precision in the estimates, right? So a quantum device, it cannot compute permanence in a useful sense. It does kind of like under the hood, like nature is computing the permanent, but you don't get to see what it is, right? And that's good because we don't think quantum computers can solve even NP-complete problems, let alone Sharpie-complete problems. So that's one thing, right? So you're not going to use quantum computers to solve those problems, we don't think. Now, there are other examples of these computational advantage proposals that are based on other Sharpie hard functions. As you said, like partition functions. So there's one version for like IQP circuits, which is based on the completeness, Sharpie completeness of partition functions. I think the random circuit sampling thing that Google is doing is also based on some kind of Sharpie complete problem that's basically just like estimate the probability of a quantum computer. So, you know, like there are other proposals that are based on other Sharpie hard functions. I think the reason why this one was noticed first is because the permanent arises extremely naturally when you're computing these things. And I think like Scott Aronson said that Valiant is the one that studied the permanents originally in several decades ago. And apparently immediately when he defined the permanent function and studied its complexity, he already knew that bosons and fermions had like this distinction, but he didn't know what to do with it. So like even at the beginning, people said, you know, that's funny that bosons have like this, are based on this permanent, which is a really hard function. What do we do that? Don't know. And then it took like 30 or 40 years for someone to kind of formalize that.
Okay, so thanks for the nice talk. So I have a question, like, so it seems like the probabilities, like the complexity of the problem is, I don't know, somehow it influences the probability. So like there, for example,
right.
I don't know if this is true, but like the idea I have is like, for example, if you have two experiments trying to solve like different complexity problems,
yeah,
can you somehow tell from the statistics the complexity of the problem or no?
No, I don't know. No. I mean, it's not obviously. And that's what the kind of part of what I was replying to Rafael is that, you know, like since these things are not observable, because probabilities are not observable, right? You cannot use the quantum computer to actually estimate this hard function. It's hard to say exactly how much information about the hard function you get just from the statistics. And that's why you need like 120 pages to prove that this thing is hard, right? Because you can say, oh, this probability is hard to compute, but the quantum computer is not going to compute that either. So there's a lot of work in saying, oh, the fact that this is hard to compute implies that it's hard to sample from this probability distribution. And that extra step is what maybe kind of breaks that connection you're asking, right? You can say, oh, it's hard to compute it's hard to sample from this probability distribution, but being able to sample from it does not tell you anything about what the probabilities individually are to sufficiently high precision to solve a very hard problem.
I see.
Something along those lines. So it's yeah.
Okay.
It's kind of obscures the connection between the two things a little bit.
Thank you for the talk. I have a very naive question because I'm not in the field.
Sure.
Basically, when you start from S, for example, state S, and go to T,
right?
You start with bosons, for example. However, I was thinking it's not possible that you have transitions like particles becoming fermions and so on in the middle of the process. And if it would change the final result. I mean, it could change, for example, it could happen some kind of transition and then it go back, and that's at the end of the day, it doesn't change, but.
I mean, okay, so you know, like at least for normal particles that you meet in the lab, that doesn't happen, right? I mean, you could imagine that as a model of computation. You know, kind of particles, that doesn't happen because of like super selection rules, and you know, some are kind of like integer spin and half spin and stuff, right? So if you're using photons, they're not going to spontaneously become fermions halfway through. But you could imagine that as a kind of computational model, right? What would it mean, you know, if that was physically possible? What would happen? And then I think you would have to know the details of that transition, right? Because what would happen is you start with your bosons here; they're in a kind of specific Fock state. Halfway through, they're not anymore, right? So you're saying, oh, halfway through, they've evolved a little bit, and they are in a very complicated state, and now they became fermions for some magical reason that we don't understand.
I mean, in this case, you would need to know exactly what you're doing, right, with the state. For example, in this case, your gate, let's say, it would be a type of gate that changes boson to fermion.
Exactly.
And
but
then you would have to know what kind of interaction is going on.
Yeah, but the thing is that, to me, what seems to be the most immediate thing that you would have to worry about is that kind of, if they became fermions halfway through the circuit, let's say, then the input to the new problem that you're defining is an extremely complicated, entangled state in a superposition that looks awful, right? So this doesn't have a simple description. So when we talk about kind of simulating the system, it's because like the input has a simple description, the output has a simple description, the circuit has a simple description, and yet computing the probability is hard.
Okay. So
but if you're talking about this other problem where the input doesn't have a simple description anymore because you're talking about something that halfway through became a fermion, I would expect that would be just as hard as this case.
Okay, because I was thinking, for example, to like, it seems, if I got it right, the calculations for bosons in principle should be simple, because bosons are simple particles, let's say, at least the scalar ones, but it turns out that for fermions it's simple to calculate. So if you could have this type of transitions even in the middle of the thing, it would like speed up your calculation, or I don't know.
Maybe, yeah. I don't know. I mean, the reason I think that it wouldn't is precisely because of that, right? Because what's simple for fermions is computing the transition from a simple state to a simple state with the interferometer in the middle, right? But if I can actually show that if you change the input state here and use a very complicated, I think called a magic state, use a very complicated sphere at the input, then it's not actually easy to compute anymore because of the state. So the statement of kind of simulability involves all the steps of this experiment, like inputs, transformations, and measurements. And the thing that you're describing kind of breaks that halfway through, right? You're saying like the inputs are now complicated. That's why my intuition is that that wouldn't help.
Good. More questions? Well, if not, let's thank Daniel for the great talk.
Thanks.